Hello and welcome again to my physics online video lecture series. Today's video we're going to be talking about a device called a velocity selector. This is basically an application of the Lorentz law force which acts on a moving charged particle. So we can begin by recalling what the Lorentz law force is. So recall that the Lorentz force F sub L is simply defined as the sum of the force from the electric field plus the force from the magnetic field acting on a moving charged particle. We can also recall exactly what these two other forces are. The force from the electric field, of course, is the charge times the electric field strength. The force from the magnetic field acting on that same particle is the charge times the cross product between the velocity vector and the magnetic field. Now the Lorentz force basically works to allow us to make a thing called a velocity selector as follows. So consider a setup in which we have, let's say, a pair of parallel plates, and I'm drawing them from the top. And for this pair of parallel plates, I'm going to apply a voltage between the two. So essentially that means that I'm going to have an electric field. I'll draw that in red like so. So the electric field is basically this nice uniform field that runs from one plate to the other. And the plates need not be square shaped. They're maybe like rectangular shaped. They're kind of short, but a long distance along which a particle goes. There may be an aperture placed on either end of the plates, like so, that a particle can move through. Okay, so this basically just is blocking particles from going in. There's an opening here, and at the other end I'm going to place another aperture. Whoops, my program seems to want to auto draw some stuff for me. But if I place an aperture over here on this end as well, then only a particle which runs straight through will sort of make it out of this little box. Okay. Now I'm going to add to all of this a magnetic field. So what I have here is an electric field E, where E, could be given by delta V, the voltage, over delta X, the distance. So if I were to sort of like label a distance between these, this right here maybe would be my delta X. Alright, so that is my E field strength for a uniform electric field. Let's add to it a magnetic field. We'll make the magnetic field also uniform, and the sort of salient feature of the magnetic field is that it needs to be within this region that I've just described here. All right, so we have a uniform electric field, we have a uniform magnetic field, and we have down here a particle which is going to enter into this velocity selector. The particle has some velocity v, it has some charge q. Alright, I'm redrawing my electric field just to get it to not have arrows kind of overlapping too badly. My electric field here is pointing from right to left. My magnetic field is pointing up out of the screen at you. My particle is moving with some velocity in the vertical direction, sort of like up along the screen. So now we ask, what direction of force does each of these two, the magnetic field and the electric field, apply to this particle? So I'm going to do that by way of drawing on a couple arrows for force. We'll do an orange arrow for the force on the particle. Say, like, what if the particle happens to be right here, for example? Then I would have a force in this direction due to the E field. So this would be the Q times E part of the force, F sub E. And then I also have, by the right-hand rule, particles moving upward, magnetic field is out of the page. I have a force in the opposite direction. Of course, my right hand is maybe reversed relative to the orientation of the screen. So force upward, you get a force in basically the opposite direction. So let's draw that in like a light green. So in this direction, I have F sub B is QVB. We could add in a sine theta if we want to have this magnetic field skewed in some particular direction. So we could say sine theta parenthetically if we want to include that. Now, we want this particle to move through this opening and then pass out the other opening. If it doesn't, in other words, move in more or less a straight line through this region, then it will tend to deflect either to the left or to the right, and as a result, it'll tend to basically hit the sides of the aperture or the sides of the selector rather than passing straight through. So what is the condition for straight line motion? Straight line motion basically means it doesn't move left or right. Okay, well, thinking back about Newton's first law, basically what this means is that we need to not have a net force to the left or to the right. We could have a net force upward or downward, but we really don't want that either. For most applications of this, the main point is no left or right. And if we do have a force upward or downward on it, then that will tend to eventually create a left or right force, as it turns out. So we really need no force on this particle at all. So sum of forces equals 0 is the condition. This implies, looking at the directions and everything, that Fe plus Fb, or in other words, the Lorentz force, Fl, should be equal to 0. Okay, it's moving quickly enough and gravity is weak enough in this case that we can treat gravity as 0. Okay, again, looking at the diagram, Fe is in the leftward direction, Fb is in the rightward direction, so we can write something like negative Q times E, that would be this one right here, plus QVB, parenthetically we have a sine theta, that would be this force here, is equal to 0. Alright, add this to both sides of the equation, reverse the sides, you get, write out the equation, you get Q times V times B times sine of theta is equal to Q times E, and that means that V is equal to, I can cancel off the Q's from both sides, V is equal to E divided by B sine theta, or B times sine theta. So this right here is your velocity, which will make this happen. So that's why this is called a velocity selector. It has selected a particular velocity. Particles with this velocity will make it through this chamber. Particles that do not have this velocity, E over B times sine of theta, will not have this, will not make it through this selector. They will be sort of like rejected via being slammed into one or the other wall, or at least into the sides of the aperture. Typically, by the way, the value of theta is 90 degrees, and therefore sine of theta is 1. And so typically we just have V is E over B. Let's work a quick example. All right, suppose we set up this velocity selector by putting two plates, applying a bias voltage of 500 volts between the two plates, making them be a centimeter apart. You can call that 1.0 centimeters if you'd like, just for 2 sig figs. And then we have a magnetic field of 200 Gauss with all vectors being perpendicular, basically matching this diagram. All right, so there's actually kind of 2 steps to this because this right here is a delta V and this right here is a delta X. And so if you want to get V is E over B sine theta. Theta is 90 degrees here, and so that means that V is just E over B. But E in turn is given by this delta V over delta X. So what we have is 500 volts divided by 1 centimeter, which is 0.01 meters. And so this ends up being 50,000 volts per meter. So 5.0 times 10 to the 4 volt per meter. And of course, this right here has to be converted over into meters from centimeters. That step I just kind of did. All right. The other thing is that we're given a B field, B of 200 Gauss, but you need that in Teslas. So that becomes 2.0 times 10 to the minus 2 Tesla. Remember that it's 10,000 Gauss to a Tesla. All right. Therefore, our selected velocity, little v, is E, that was 5.0 times 10 to the 4 volt per meter, divided by B, which was 2.0 times 10 to the minus 2 Tesla. And so my selected velocity comes out to 2.5 times 10 to the 6th meters per second. And you'll notice that that is independent of the charge of the particle as long as the particle has non-zero charge. If the charge is 0, then this won't work anyway. All right, some basic comments on this. Our system is not flawless. That's the first comment. There's going to be some margin of uncertainty. Here's why. In designing this system, we've made some assumptions. We've assumed that the particle has to go absolutely straight in order to make it out of this. There is, however, some wiggle room. The apertures both have some size. The top aperture and the bottom aperture do. And what that means is, in principle, I could have a particle that rather than entering here as drawn, could maybe instead enter over here on this edge and be deflected very slightly by the magnetic field so that it comes out this edge. Notice that it's made a slight deflection here. And likewise, I could have it enter on this one and make a very slight deflection. Sorry, this would be an electric field deflection. I could have it enter here and have a magnetic field deflection as well. And so I could start off right here and end up having, instead of a straight line, a deflection that causes it to leave this way. Okay. I could also, in principle, have a particle that starts off with a velocity like this that enters through somehow, and then I get a deflection from the B field so that it leaves straight through here. So those are some limitations. That's all.